Hello student, welcome to our physics discussion, that is physics in a smart way. In our last video, we have started to talk on oscillation, that was simple harmonic motion. Now we start to go into the details of it. In that context, I am, you can say, forced or willing to deviate from the regular way that is given in your NCERT books, because that is mathematical, and that if that loses the sense of physics and the practicality, then talking pure mathematically, we cannot create physics. Yes, we know mathematics is a helping tool for physics, but physics is not mathematics. It's not all about mathematics. That is something else. So thereby, I'll be deviating from the way that is given in your NCERT books, but after the whole thing is over, you will be getting a proper knowledge of everything, and then you can follow your NCERT books or whatever textbook you are having, then you will have no problem. So don't fear that I am taking you in a different way or different direction or something like this. So that is not to happen. That is not because we will be discussing physics here, and that should be your 11th level physics, and that too simple harmonic motion. Okay, so so far as simple harmonic motion, as you have discussed, that's a oscillation, that's a vibration. And as I told you in the last class, our approach will be just in the opposite way as you do in the other topics. We'll be starting with some real motion, then we'll be trying to create a hypothetical motion. But before that, let me show you something. Let us say we consider a simple pendulum. Simple pendulum. B is the middle position, where if the bob is kept at rest, that will be remaining for indefinite amount of time. If you disturb it from the position of equilibrium, or that is B, and then release it, then you know the pendulum will start to vibrate. Let us say we have taken the bob from B to the position A, and hold it there. And for all future calculations, all future discussions, A will be our starting point. The moment I release from A, we know the bob will be starting to swing down, crosses B, but by the time that reaches B, that must have acquired a velocity, which with the help of inertia will be pulling it, will be pushing it onwards. Finally, that come to rest at C, which is a point equivalent to point A. So thereby, and then the bow starts to swing back, and then the oscillation will be there. That's oscillation. If the angle that it makes with the vertical, the extreme position either at A or at C, at the extreme position, the angle that the string makes with the vertical is less than, sometimes books take to be 8 degree or 10 degree like that, then thereby the path of the bob, which we know clearly is the arc of a circle, but that looks almost like a straight line, So then we can consider it a simple harmonic motion. You can consider that the bob is moving on a straight line, that is ABC, A, then B, and then C, and that is almost a simple harmonic motion. For other angles, that's a harmonic motion, that's oscillation, but that oscillation won't be simple harmonic. And at this juncture, we shall not discuss that, because that takes time and space. Okay, so thereby, that is a practical oscillation, which is a simple harmonic motion if the angle theta is small, as I told you, less than 8 degree or 10 degree in some books. So, but here in figure 2, that was your figure 1, and this is your figure 2. In figure 2, what we consider, we try to create a hypothetical SSN from a real motion which we already know. Let us consider a bob-like thing or a circular object or a small mass. In our case, it must be a particle. Of course, my drawing quality is very poor and that looks like a lump, an ugly lump. But anyway, we shall manage to pull on with it. We consider a just a minute. Let me pause the video and we can draw. Here we consider a uniform circular motion, an object which is moving on a circle uniformly with a constant speed. The circle is having the radius A. In future, you will be taking different shape, different color, and all that. But for us now, A is the radius of the circle. This body is here. That is the starting point. When you start to take your observation, t equal to 0, time t equal to 0, body starts from here, and the body moves on the circular path with a constant speed, and the speed is given as u. That's because in case of rotation study, you know that speed of the object or velocity equal to angular velocity into radius, v equal to omega r. So here, angular velocity, if it is omega, and the radius equal to a, so u equal to omega a. That is the equation 1, which you know in case of rotation. As you know, omega, angular speed, omega also will be assuming different color later on, just like a, but now it is angular speed. Okay. Because the body is moving or having a uniform circular motion that moves around the circle with radius a with a constant speed, so the motion will be monotonous for us because there is no variation, but mathematically simple it is. So thereby the speed is constant. So angular speed or omega here also we can express as the rate at which angle is covered. The rate at which angle is covered also will be constant. So in place of using sophisticated terms like omega equal to d theta by dt or something like that, okay, just for style's sake, can avoid that, dispense with that, omega equal to theta by t. If theta is the angle covered, angle made at the center in a time t, so that angle is covered at a constant rate. Every second angle coverage will be same. So thereby, that is the second factor we put in. We just try to do something, think of something, not to do something, but we try to imagine that as the body, it starts from this point where the circle cuts the x-axis, positive x-axis, and the body moves in an anti-clockwise direction. As the body starts to move, we always imagine drawing a perpendicular from the body onto x-axis. In fact, we can do the same thing with y-axis also. We try to drop a normal from the body onto x-axis. You can do that with y-axis, the same thing will be there. With a very small change, and the thing also will be SHM, or our main purpose won't be we won't be deflected from our main purpose. But for present, we consider this as the normal from the body onto x-axis. So when the body starts from this point, we know normal is of zero length thing. Try to focus hard. As the body goes up and up in anticlockwise direction, we always think of the normal. You must excuse me, from the body onto the x-axis. As the body goes on, our imaginary normal, it's and especially our point of observation or the thing will be to look, just to focus just at the foot of the normal, foot of the perpendicular, which is drawn from the body onto x-axis. So as the body goes on, we know the foot of the perpendicular that slides along x-axis towards the origin, that thing happens till the body goes and crosses the y-axis. When the body goes beyond y-axis to the second quadrant, we know the foot of the perpendicular will try to slide away from the origin. Then when the body reaches this point, the end of the second quadrant, the foot of the perpendicular is here. During the motion of the third quadrant, you know the perpendicular foot will be again sliding from the negative x-axis on the negative x-axis toward the origin, and that will continue till the third quadrant is covered up. During the motion in the fourth quadrant, we know again the body will be starting to slide from the foot of the perpendicular will be starting to slide from the origin onto the x-axis and finally comes to rest at the point where it has started. So continuously as the body goes on and on and on around the circle, you know the foot of the perpendicular that is moving on and off, moving up and off, and that oscillates on x-axis. So the motion of the foot of the perpendicular is simple harmonic here. You have to believe me, you have to take at my word, okay, that we shall establish also. So the motion of the foot of the perpendicular is simple harmonic motion. So our intention is to study the motion of that, the so-called foot of the perpendicular. Here, the main body is real, the foot of the perpendicular and its foot, the perpendicular or the normal and its foot are imaginary. So just like I told you in the last video, starting from a real motion, we try to engage ourselves with a imaginary motion, that is the motion of the foot of the perpendicular. All the measurements we take from the origin, if we think so, then at the start of our calculation, at the start of our time measurement, the body starts at t equal to 0. Body starts from this point, the main body. Mark it. Always you must be able to differentiate whether I am talking of the main body or talking of the foot of the perpendicular or the imaginary body. As the main body starts from here, we allow it a time t to pass. So when the main body has traveled for a time t, and that makes an angle theta at the center, then you know equation 2 is valid. The theta will be equal to our omega t. The angle the main body makes at the center will be, that is omega t. And if you take our measurement from the origin, this is the position vector. This is the position vector. This is the position vector. Okay. This we can take also is the x position. So you may take as the position vector or x position, whatever it is. So we know that will be position vector is r, or you must say the position is this. Body starts from here, the foot of the perpendicular, not the body. You must be able to differentiate. So by the time t has passed, you know the foot of the perpendicular starts from this point and has arrived at the point P. So its position from the origin is the position vector, or you may say that is the x position. Both of them are same. That can be found out by using the trigonometry of the triangle that we have set here. This is a right angle triangle. We know this is again the radius equal to a. So if I consider cos theta in this triangle, now cos theta equal to, you know, that is equal to r. No, you can say r or x by your a, b by h. You can say that the position vector or x. So then cross multiplying, you can say R or X. I'm writing like this. R or X will be equal to, that is A cos theta. A cos theta. But we know, let me clear up some space for you. We know that, so we got that the position vector or the x position of the body equal to A cos theta. But we know theta equal to omega t. That is A cos omega t. That is equation number 3, the main equation that you got. So that is the first equation of SSM, R or X equal to position equal to A cos omega t. That was our basic intention. Next class will be continuing from here. Okay. So when I develop this equation R equal to A cos omega t, position vector equal to A cos omega t, somehow that looks like the equation given in your NCERT books, but in your NCERT books, you are being given a general equation. Slowly, we'll be coming to that. So don't worry. Just try to follow me, and if not clear, you can usually show your dissatisfaction with the help of your comments, so that I'll be able to be careful in the future. Okay, that's all. Thank you for your kind cooperation. Today we are off.